All right. Good evening, India. Good afternoon, Sweden, and good morning, US. A warm and heartful welcome to this insightful panel discussion. You ask, we answer. We are delighted to have gathered a group of distinguished experts and thought leaders from various fields to engage in a thoughtful, provoking conversation that promises to be both enlightening and inspiring. Get over the ideas that only children should spend their time studying. Be a student as long as you still have something to learn, and this will mean all your life. And this is me. Myself is Ankit Porwal, works for Megger India as a business unit head for Transformer segment, and I am responsible for the Power Transformer segment business for South Asia region. I have more than 12 years of experience in the era of substation apparatus testing, allowed me to successfully support a large community of customers at different commercial and technical topics. For the last 10 years, I am working for Megger and I am providing engineering consultation and recommendation to better test and evaluate the condition of substation equipment with special focus on power and distribution transformers. I am the co-author of various technical papers published in technical magazines and IEEE. I did my engineering from APJ Kalam Abdul University from UP, Lucknow, India in 2009. So today's discussion brings us together a diverse array of perspective on advanced testing technique of transformer and bushing. And we hope that we will shed light on some of the most pressing issues and innovative solution in this domain. Our esteemed panelists are well known for their expertise, and we look forward to their valuable insight and lively exchange of ideas. As we embark on this journey of exploration and discovery, let us remember the importance of open dialogue and the exchange of ideas. It is through conversations like these that we can gain a deeper understanding of the challenges we face and work collectively towards a better future. We also encourage active participation from our audience, and your question and comments are highly valued, and panelists will address all shortlisted questions during the registration. So once again, warm welcome to our esteemed panelists and our wonderful audience. Let us make this panel discussion a memorable and enlightening experience for all. So thank you for joining us, and let the conversation begin with introduction of the panelist. So our first panelist is Dr. Diego Rovalino. Welcome, Dr. Diego Rovalino, in this panel discussion. So let me put it some light on his career. Dr. Diego Rovalino is the Business Development Director, Power Transformer at Megger. His specialized in the diagnosis of complex electrical testing procedure and the strategic development of state-of-art transformer testing technology. He has over 20 years of involvement in the electrical engineering profession with management responsibility in the power system, oil and gas, and research arenas. Diego is the senior member of IEEE, a member of IEEE/PES Transformer Committee, a certified project management professional with the Project Management Institute, and the general chairman of the IEEE DEIS 2022 40th Electrical Insulation Conference. He is the author and co-author of over 40 technical papers related to power distribution and instrument transformer condition assessment. Diego receives his PhD in electrical engineering from Tennessee Technologies University while researching power system optimization with a focus on aging equipments. So welcome, Dr. Diego.
Thank you very much, Ankit. Good afternoon, good morning, everyone.
Yeah. Our next panelist is Mr. Joachim Skolding. Joachim Skolding pursued his MSc EEE from Royal Institute of Technology, graduating in the 2012. He started his professional career with the DFR, Dielectric Frequency Response, or FDS, test equipment for applied to the cables and power transformer insulation. In 2006, he advanced his career by moving PAX Diagnostic as a product manager for the DFR and FDS instrument. And in 2008, Joachim joined Megger as a part of acquisition of PAX Diagnostic, and he is now working as a product manager in transformer testing at Sweden factory. He is author and co-author of various technical papers published in IEEE and other technical platforms. So welcome, Mr. Joachim Skolden, in this particular panel discussion.
Thank you very much. Hello, everybody.
Our next panelist, Mr. P.K. Patnaik. So P.K. Patnaik, sir, is a seasoned individual with more than 33 years of technical experience in designing, testing, and commissioning of protection, control, and operational scheme, project implementation, coordination, operations, and maintenance of electrical equipment at various HT, LT, EHT level grid substations. His expertise also lies in the field of GIS, SAS, production control, and special maintenance of transformer and EHV equipment on condition monitoring assessment and fault diagnosis. He has played a crucial role in the publication of around 105 technical papers in different national and international proceedings journals. He frequently authors general publication of various reputed organizations like CBIP, EMA, Electrical Mirror, Electrical India, to name a few of many technical books on electrical technology, and awarded in many of the national and international forums. He has the best bond with the Best Engineer Award received as a Special Appreciation Award in OPTCL, Odisha Power Transmission Corporation Limited, in 2013, 18, and 2022, presented with the Best Paper Award during the International Conference Metering India in 2018, 20, and received many appreciation awards from the CBIP and EMA and other international forums. He has been a member of IEEE, Institute of Engineers. He is also admin of the a nationwide technical group named Spark, with around 6,000 engineers all across the nation, with 19 main groups and 8 subgroups. So welcome, Mr. P.K. Patnaik, in this particular panel discussion.
Yeah, namaskar.
Namaskar,
welcome to everyone.
Namaskar. Yeah. Our next esteemed panelist is Dr. Rajesh Arora. Dr. Rajesh Arora received his BTech and Master of Engineering degree in Electrical Engineering from Delhi College of Engineering, University of Delhi in India, 1999 and 2003 respectively. He completed his PhD in Grounding System Design from UPES Dehradun. He is certified Energy Manager and Auditor. He has worked in 400 and 220 kV substation for more than 14 years in company called Delhi Transco Limited, DTL. He has also worked as a Deputy Director, Transmission and Distribution in Delhi Electrical Regulatory Commission, DERC, for more than 3 years. He has also rendered his service in the SLDC of Delhi Transco Limited. He is currently working in the Design and Engineering D&D Department, Delhi Transco Limited, as a Senior Manager Technical, and he is highly interested in research area of high voltage technology, grounding earthing systems, design of power system, protection system, computer application in power system, power transmission and distribution designing, regulatory, business and affairs. So warm welcome, Dr. Rajesh Arora, sir.
Namaskar, good evening, good morning, good afternoon.
Yeah. Our next esteemed panelist is Mr. Amandeep Singh. Mr. Amandeep Singh is a 2006 alumni of DAVIET Jalandhar and is currently pursuing his MTech in Power System and Reliability from NIT Jalandhar. He currently works as a Deputy General Manager, Asset Management for Power Grid, where his responsibility includes the operation and maintenance of transformer and reactor assets. Prior to asset management, he worked with NLDC Grid India, where he gained 5 years of experience. He regularly represents India in various SIGRE working groups and is currently a member of SIGRE. He was awarded with Prestige CBIP Appreciation Award in 2023, this year itself, and is also member of CBIP editorial board of the monthly magazine Water and Energy. He has to his credit more than 17 technical papers presented at various national and international conferences across the world. He also represent India IEC oblique TC 122 and and IEC TC 123. So we all welcome Mr. Amandeep sir also in this particular panel discussion.
Thank you, Ankit, for the wonderful introduction, and I give a very warm welcome. And I hope this panel discussion is informative for all the participants. I see more than 100 people have already joined.
Yes.
And I think if we are done with the introductions, Ankit, then maybe we can jump into some
Yes.
business.
Correct. So let's
Thank
start with the with our first question of this panel discussion, round one. And the first question goes to our first panelist, Dr. Diego Rovalenu. And the question is, what are the failure symptoms of dry type transformer? How to go for predictive failure assessment of dry type transformer? Question to Dr. Diego.
Thank you very much, Ankit. And that is a very interesting question because especially for dry type transformers, can you hear me well? Can I get a thumbs up? Is everything okay? Thank you. So basically,
Yes.
a dry type transformer is a sensitive unit, and we need to understand what kind of dry type transformer are we talking about. Is a one type? Is a encapsulated type? What is the type of application that we have for this transformer? One of the things that we have done for many, many years is insulation resistance test, right? A very typical and practical test, where actually we have identified some differences in the way that the transformers have been tested in different places and according to different standards. One of the things that we have also identified is the lack of knowledge about the use of guarding systems on the insulation testing devices, which allows you to better characterize different capacitive regions of your transformer. So when we think about these devices, of course, very simple is the electromechanical part with electromechanical analysis, with our, basic type of testing from ratio testing, winding resistance, short circuit impedance, very, very important for this type of devices, and capacitive analysis. We can have a good understanding of what is the situation of the unit. But keep in mind that things like, you may say power factor or tan delta might not be a direct measurement. But if you do a step up or a tip up test based on dielectric response analysis, that would be a much more informative process. The other one that could be applied as well is partial discharges on dry type transformer testing. So those are the things that we will be looking at, especially if there's some overheating, deformation of the windings. If there was a through fault, let's look into the condition of the winding, short circuit impedance, something very simple, very practical, very fast to understand what the condition is. If we need to get into something more complicated, we can go into SFRA testing, look at the full frequency response. And from the dielectric point of view, we're not looking into, the beauty of having an oily impregnated transformer. We have oil to extract and do some additional analysis. But here we need to deal just with the solid insulation material. And for that, things like tip-up testing, insulation resistance is a good way to characterize the condition of the transformer on the dry type. Thank you.
Okay, thank you. Thank you so much, sir. Now, the next question to our next panelist is Dr. Rajesh Arora. Sir, question is how to conduct DGA test and what is the superior technology available in the market? And if C2H2 is beyond limit, then as per DGA, what should be the corrective action?
Thank you, Ankit, for this very informative question. And with that answer, the people will get benefit. How to do DGA is very important thing.
Yeah.
And I am talking in reference to India. First of all, the DGA starts with proper sampling. The moment you get the sample, you have to extract gases. After extracting of the gases, you have to quantify, you have to do the analysis. After analysis, you have to do the interpretation. And after interpretation, you have to identify the fault based on your analysis, and then you have to take corrective action. This is the basic fundamental.
Your voice is missing, sir. We lost you, I think.
If I think we lost Dr. Aurora, I cannot.
Yeah. Okay, we will park this question maybe here, and we'll take it after he will join again. So the next question for our next panelist to PK Patnaik, sir. And the question is, sir, which parameter of transformer oil decides its life, and what is the criteria for changing the transformer oil in service?
Yeah, so good evening, everyone. Once again, I'm PK Patnaik from this side. Basically, this question is, in one way, I can say, relating to the life of the transformer. And as we know very well, whenever we go for any fault analysis, we go for the DGA. And on the base of this life assessment, whenever we go, as per my knowledge goes, we should advocate for hydrogen and methane, because this hydrogen and methane, the gas, it evolves out with the temperature of 150 to 300 degrees centigrade. So that will be one of the way to decide the major part and to play the role as per the life is concerned. But the other key gases are also to play the important role, out of which the water content, if I just consider, though it is not the part of the gas evolvement, but still water content also the other part we must have to consider. But whenever you go for the diagnosis of all these things, the major role is being played by the composite insulators, because composite insulations, what you have, oil we have, paper we have, then solid woods we have, stacks, solid stacks we have, but major part of the that oil itself remains in the paper insulation part. So in this context, I can say if you go for the criteria, suppose if it will be asked someone that when we should go for changing of the oil of the transformer, then I can say one point we must have to consider the water content in the oil. Then it's the interpretation, what should be there to the paper, because if water content remains in the part of oil is of same x ppm, then in the paper it will be of like 98%. I mean, if it is 100% wise we go for, then 98% of the oil itself remains in the paper part. So just of knowing that oil is having some quantum of water, we cannot exactly guess that the total is of having that much. Second part and most important one is that regarding changing of the oil, we should think about the particularly ton delta value of the total oil and all. That is the second part. And the DGA result, especially availability of hydrogen and methane, that should be also clubbed up. So these interpretations, if we consider, finally we can conclude that this oil need to be gone for replacement and all. But in one aspect, I can say the oil in DGA, whatever the key gases we are getting in the oil, cannot decide regarding the life of the transformer, because for that sake we need to go for like DP analysis, DP paper analysis, and Furan analysis also. So that should be having one sort of interpretation of those threshold limits. If that threshold limit goes certain way, then we can proceed. But in one line, I can say that one is of our hydrogen and methane gas availability, and second was the water content and the Furan analysis method. That's all from my side.
Thank you so much, sir. Very nicely explained. So we, I mean, before this, we lost Rajesh Arora, sir. So I'm coming back to him once again and repeating the question for him. How to conduct DGA test and what is the superior technology available in the market? If C2S2 is beyond limit as per the DGA, then what should be the corrective action?
Okay. I have already explained there are basically 9 gases we usually extract from DGA analysis, and based on the analysis, we decide what action to be taken. First of all, we have to identify the gas. And it is very pertinent to mention here that still in many utilities, IEEE C57 104 2008 is being adopted, and it rely on the key gases only. And I have seen the reports given by many utility that talk about the key gases, and there is one table is there that decide the condition of transformer. My request is, if we want to move in a forward direction, we have to adopt IEEE C57104 2019 version, and it talk about three status 1, status 2, status 3. And important part is it always analyze data based on the oxygen and nitrogen, whether your transformer is a breathing or non-breathing type. It again analyze based on the age of your transformer, and it has four tables, and it has very good elaborated flow chart that is to be implemented by all the utility to arrive at a decision what to do further. Talking about C2H2 acetylene gas is there, that clearly indicates the very high temperature above 700 degrees Celsius, and you have to closely monitor your transformer once you get it, and you have to look at the rate of change of that gases. If that is more, definitely you have to go for the internal inspection. That indicates that there is some fault, major fault, arcing is there inside the transformer and creating temperature of more than 700 800 degree, and there may be carbonization also. Based on that thing, you have to take action. And finally, I again repeat my sentence, C57104 2019 version to be adopted. That is the new version, and you will get a new idea how to move further. That's from my side.
Thank you so much, sir, for nicely explained. Now, next question goes to our next panelist, Mr. Amandeep Singh from PowerGrid. Sir, the question is how to determine life expectancy of power or distribution transformer that has been in service for 50 years with 50% load.
Right. Okay. Thank you, Ankit. And very interesting question. I mean, I don't know who has given this query, but seems that it's a very specific question. He has a transformer which has already crossed 50 years of service life and about average loading of 50%. So this is a very seems to be a very specific question and for a specific case, but I'll try to generalize the answer for the benefit of all participants. So let me just simplify. See, the life expectancy of a power transformer depends on many factors. If we consider, first of all, the approach, then we have to first do the condition assessment, and based on it, we can predict what is the condition of the transformer. So when we analyze the transformer, we have to analyze from the perspective of each and every failure mode. The failure mode can be a dielectric failure, it can be a thermal failure, it can be a mechanical failure, it can be a failure related to the OLTC of the transformer or the bushings, and lastly the oil. So these are the major 6 failure modes that we need to address when we try to analyze the health of a transformer. And once we analyze the present health of the transformer, we'll be able to make a prediction about how much more life we can expect out of that transformer. So speaking specifically about PowerGrid, our oldest transformer, which is in continued service, is was manufactured in 1984, and it has already given us 39 years of service. So when we talk about specific things that we need to monitor, so one of the factors, obviously, the in the question, this loading is one of the major factor, because I'll just quickly say that if the transformer is, when it is designed to have heat being produced. So at full load, the heat being generated in the transformer would be dissipated ideally if the cooling system is working perfectly fine. But at 50% of the loading, only 1/4 of the designed heating, because I square R losses will be squared off. So only 1/4 of the designed heat would be generated inside the transformer. So this is one of the factor. So from thermal point of view, our transformer is safe. But then we have to consider other factors. Factors like the loading, and it would be supplemented by the paper integrity. For paper integrity, we would need to do the Furan analysis. We can do the advanced aging marker test like methanol marker test. And then we will also have to analyze the temperature. Even if our transformer is being loaded at 50%, but our cooling system is not working to its full capacity, it's not functioning properly, the fans are not working, the oil circulation through the pumps is not happening. So in that case, the temperature inside the transformer would be going beyond the limits specified for the paper. So there will be accelerated degradation of the paper. So in those cases, even when our transformer is at 50% load, still the heat being generated, and because this heat is not being taken out of the transformer, it would affect the paper inside. And lastly, oil condition would also have to be considered. And Mr. Patnaik also described the condition of the oil. So I would just like to supplement his answer that besides the basic test for oil condition of a transformer, the basic tests are BDV and moisture. And then we can do some other tests like acidity and tan delta or IFT test, which are other important tests. But then we also need to analyze the particle count inside that oil, which would also indicate how much degradation is happening. And then there can be some advanced tests like corrosive sulfur test or density or pore point, flash point, oxidation stability test. So these tests will also indicate the true health of the transformer and whether it is fit for continued service even beyond that period which it has already given us a good service. So I would consider all these parameters in addition. That means the moisture inside that transformer oil, the integrity of the paper, and the average temperature of how much heat that is being generated. So these factors I would consider besides the loading criteria, and only then I would be able to make a recommendation on what is the condition of the transformer and how long more it can be continued to be kept in service.
Thank you so much, sir.
If you
Yeah.
if you allow me to add just a couple of words to what greatly was described by Mr. Amandeep, I fully agree with him on that. But I also want to add that don't forget about the accessories and the additional pieces of equipment that we have on that transformer. If we had it for 50 years, it's not only what we have inside the transformer, but look at the bushings as well, for example. I don't know about the cooling system, what kind of cooling system they have, if they have some pumps or if they have some additional, the LTC, do they have an LTC? So look at the transformer from the overall picture, right? It's not just the internals. It's absolutely well described the way that Mr. Amandeep described all the issues that you can have with moisture, the liquid insulation, the solid insulation. But if a bushing fails, right, everything could be even okay, and we can have a low loading factor for that transformer. But still, so take a look at the additional pieces of equipment that are components of your transformer. Thank you.
Yes, I described the 6 failure modes that are majorly involved: dielectric, thermal, mechanical, and besides that, OLTC, bushing, and oil. So besides these 6, the accessories, of course, would account for one another factor which we would assess for evaluating the health of our transformer. So in totality, for arriving at the big picture, we'll have to zero down on the smaller components of the pictures, and then only we'll be able to see the larger picture in totality.
Thank you so much, sir. Sir Diego and Amandeep sir for the wonderful answer. And moving to the next question, and the next question goes to Mr. Joachim Skolden, and the question is, what is the significance of demagnetization, and is there any process to recognize the transformer is demagnetized or not post winding resistance measurement?
Thank you, Ankit. It's also a good question, and here I would like to make clarification, because sometimes when I is in the field and testing transformers, you must clarify that there is a difference between a discharge and a demagnetization, because you said post winding resistance. And when you do the winding resistance, you will of course put a lot of energy into the transformer. And once the winding resistance test is done, you will then have a discharge. That is not the same thing as the demagnetization. So once the winding resistance is done, you will have a magnetized core. And what is the significance of demagnetizing the core? For me, there are two main reasons. One being a magnetized core will influence a lot of the tests that you do. So in order to have valid results for all your tests, you should have a demagnetized core. The tests that can be affected is like the SFRA. If you do excitation current or turns ratio, they will all be affected if the core is magnetized. So then it is very, very, very important to have gone through this procedure. How can you verify that the core is really demagnetized? Well, there are the most obvious answer is, of course, to do a magnetic balance. The magnetic balance test is a very, very well-established test to make sure that you have symmetry between the different core legs, making sure that you have a proper demagnetization. You can also get a small indication of your magnetization status if you happen to do turns ratio or really excitation current, because if you look at the excitation currents, they will be very symmetrical, at least the outer phases in a really demagnetized state. It is not as accurate as the magnetic balance, but it will give you an indication anyway, and it is a way of helping you to assess this. I hope this is a clear enough answer.
Yes, Joachim. Just would like to add one more point here. As you rightly mentioned that all the testing related parameters is going to disturb, and that is one of the major drawback. And when it comes to the operational part, sometimes it has been observed by the utility engineer when they are going to charge the transformer back to the service, it may trip due to the inrush current because of it is already magnetized. So that has already been reported by most of the engineers during the operational. So this is one of the operational disadvantage. So yes, thank you very much,
Definitely,
Joachim, for
definitely.
addressing this question. Yeah. Now we starting round two, and again back to our first panelist, and the question goes to Dr. Diego. The question is, Dr. Diego, for you. What are the available online sensors and techniques for preventing surprise failure of oil-filled large transformer in the industries?
I got a little bit of a broken communication, but if I understood correctly, the question about online. There are many things about online monitors, and you can have
You want
like
me
a
to
Christmas
repeat the
tree
question?
as a
You want me to repeat the
yes,
question?
please.
Okay, sure,
If
I'll do
you
that.
could, please.
Yeah. What are the available online sensors and technique for preventing surprise failure of oil-filled large transformers in the industries?
Okay, thank you, Ankit. And again, what is a surprise failure? That's something that is coming pretty sudden to our system, right? Something that we did not expect. And one of the main things that I think we as specialists in the area of testing and promoting the extension of life of the transformer, right, and different pieces of equipment in the field, we try to be proactive and not reactive. right? And this proactivity that we look at is based on not only online, but also offline technologies. If you think about some of the sensors that we could incorporate in our transformer, there could be so many, right? Let's start from DGA, for example. What kind of DGA analysis do I need? Do I need some historical information? And sometimes we need to have a culture of asset management in our facilities, in our utilities, to properly understand not only the numbers, right? We may have some limits, but we need to understand from the energy point of view, what is the meaning of those gases, right? It's low energy gases, it's high energy gases. So there's some electrical or thermal effect internally in our transformer when there is an active condition, when the unit is operating. And because of that, we can identify we have some partial discharge activity or is a thermal activity. If the problem could be coming from the core or from the windings or from the paper or from the liquid insulation. But everything is related to energy. If we can detect, for example, we can have a very simple device as a Buchholz relay, right? If there is generation of bubbles, generation of gases, well, the Buchholz relay will give you the first flag, right? The first indication that you have a problem. Well, investigate, right? Don't just evacuate the gases from the Buchholz relay. You have to continue. You have to learn what's going on. If you have some gas detection, let's say, so you have some changes in your hydrogen, methane, ethane, acetylene, whatever the gas is, you need to understand why is that change, where is it coming from, how to better interpret the results. And like Dr. Rajesh Arora properly explained, IEEE 57104 2019 did a very interesting job on the new publication. One of the most interesting things that was on that publication is not saying that the transformer condition is, what it's saying is the oil condition is, the status of the oil is this, because there are different components that could be interrelated. So as I mentioned before, when Mr. Amandit was doing his presentation, we can have DGA, we can have partial discharge, we can have thermal control. And I think that temperature is one of the most critical parameters. We can have some humidity control, right? We can have some moisture analysis. All that is okay. But the evolution of the process, the application of the transformer, the condition under which this transformer is working is the responsibility of the operator, right? And sometimes we see that limits are exceeded, changing in conditions are variable, and we start just removing these units because we get a false alarm. And it's not a false alarm. You set the limits, but the changes internally need to be well understood. That's the reason why, to me, a good compromise is taken when you understand the offline testing together with the online testing, and you can match that information together to have a good comprehensive understanding of the health of your transformer, right? And like I said, not only the cold winding system, but also the accessories. Bushings, I think, is one of the most critical components right now. We have seen several situations where bushings failed after good testing, right? And you cannot do online DGA on your bushings. Actually, you cannot do even sampling of oil sometimes on your bushings unless you do a very formal procedure, which is something that some of the major manufacturers may not like you to do. But be careful about it. So offline together with online is the best way to be proactive and prevent those unexpected failures in the field.
Thank you so much, sir, for very impressive answer on the tricky question. Thank you, and you did very well explained in general way of for this particular question. So the next question goes to Dr. Rajesh Arora. So the question is, what is the limit value for C2 in transformer bushings? Okay.
First of all, Ankit, I would like to mention here that we have to go through some documents like figure 755. That is about transformer bushing reliability. Then comes IC 60137.
Yeah.
If you look at the clause number 4.10, it talks about the maximum limit of C2. First, we have to understand what C2 is. There are basically two capacitance in the bushing. One capacitance is up to the tap, and second tap to flange, that is grounded. that is C2. C1 and C2 plays very vital role when we are going to measure the tan delta. Now the value, the maximum limit as per IEC 60137 4.10 is 10,000 picofarads. But I can tell you one thing, there are two types of bushing. One is with test type and second is potential type. In India, we are using test type bushing presently, in the present scenario only. In that case, C2 is usually equal to the C1. It is in the range of 500 thousands, depends on manufacturer to manufacturer, but the maximum limit is yes, 10,000 picofarads.
Thank you, sir. The next question is to Patnaik, sir. Sir, the question is it mandatory to measure tank current for distribution transformers during short circuit test? Of course, it is required for power transformer.
Yeah, actually, let me to answer in this way. Basically, it depends upon the user or utility users. If they demand, then it could be considered as the tank current to be included in the short circuit test. But as per mandatory way, we say it is answer is clearly say no. But some utilities right now they demand for to have this particular one inclusion in the short circuit test. And especially what happens if it is not there even in the short circuit test. But my recommendation goes if it will be included in the kind of facilities to the transformer, might be of distribution transformer or power transformer or the big transformers what you have, then it could be easy to know the kind of fault occurrences what it is happening internally. So it is quite way, and I should also take up this point with Megger unit. If you go for such kind of a kit to develop, then automatically maximum of the people across the globe, they will be benefited, because the tank current itself will be indicative towards any kind of things happening internally. It could be diagnosed along with also this DCA we do to take those oil and to get analyzed. So it's my way say answer is no as per the mandatory for the distribution transformer, but we should have such facility. That is one of the good way to go for. That's all from my side.
All right. Thank you, sir, for answering this question. Moving to the next question, which is for Amandeep, sir. Very good question. Sir, what is the latest testing technique of or trends in the power transformers?
Okay, thank you, Ankit. Another very, I mean, this question in itself is almost like a seminar on itself, but I know
Correct, sir. Correct.
time would not allow me. So I would just like to quickly summarize. So first of all, before we talk about the latest testing techniques, we first need to, from an asset manager point of view, we first need to finalize what are the latest approach towards asset management. So once this approach towards asset management is fixed, then we have our gaze fixed on what is the end result that is required by any utility. Now every utility needs to decide on its own what is the best approach towards asset management. So if we talk strictly about power grid is now transitioning from a conventional condition based monitoring to a reliability centric maintenance scheme, where we are first of all identified and targeting our correct assets which need our proper monitoring. And we are also transitioning from the conventional offline monitoring to online. So Diego also just briefly touched upon this. So once this approach is finalized, what is to be done, then we need to do out the specific requirements which we need to, once we have identified the candidates which requires the most critical monitoring, then we can target what needs to be monitored. So this techniques that we can implement can range from a conventional DGA. So like we have transitioned from the conventional DGA to even the online DGA monitoring. Then we can do the aging marker test. Aging marker as in first or initially we used to do the methanol marker test is the latest technique that we are adopting, because this is a transition from the Furan analysis. So Furan indicates aging of a paper at a very later stage. Methanol marker would give a signal very early on when the aging is just starting. So this is the latest marker test that we have adopted. Then sweep frequency response analysis, which would be able to pinpoint the mechanical stresses that our transformer is experiencing. So all this SFRA, then dielectric frequency response, or FDS, that is another latest technique which has benefited us immensely, because earlier it was very difficult, and I have many instances when we have uh, we have worked very closely with even Megger also and other teams, where we had some doubts about the condition of a transformer, and because the conventional tan delta test would give you only a the results of tan delta may get affected by other factors. So by doing the DFR test, we were able to pinpoint that the transformer winding is absolutely healthy and tan delta values are getting erroneous value due to some other factors. And lastly, that online PD monitoring, which is the latest trend, and everyone is now focusing more about online PD monitoring. There are many techniques, and PowerGrid is also experimenting with this. So these are the major tests that we have adopted, and we have got immensely benefited from these tests. Our availability and our equipment, we are able to pinpoint the defects very early on. So I would suggest that to every asset manager, every utility, that first you need to finalize your approach. And once your approach is fixed, then you need to finalize a test that you need to adopt. So which would give you the maximum result. So that's all. I would like to just, thank you.
Very, very impressive answer, sir. Thank you so much. Yeah. Moving to the next question to Mr. Joachim Skoldin. So the question is, with the help of comparison-based SFRA measurement, it is possible to accurately identify the transformer winding having very minute geometrical deformation or very minute interturn shorting in any one or more than one of the windings.
Oh, it's a very, very difficult question. When we talk about SFRA testing, it also reflects back to the previous question about demagnetization. And there are a few things that I would like to highlight here. You have phrased your question in a very, very good way, because you say comparison. And when we talk about SFRA, it is a comparative test. A comparative test. And the whole foundation and the basic is you have a reference measurement. That reference measurement should be taken when the transformer is in a very, very known good condition. Once you have that reference, it is very easy to make a comparison. Your comparison-based measurement will find the minute differences. However, what is very, very often the case is you do not have that reference, and that creates the questions or the doubts. But as long as you have started taking your reference measurements early and you have a very, very good base or a good foundation for your SFRA testing, you will find the minute changes. It is also going back to how you take the test. If your transformer is not demagnetized, it is directly shown on the interturn fault. If I can say it like that, the magnetized core will give you an answer in the SFRA test like it is almost showing up as an interturn fault. So that is a very, very, very difficult task, and you really must make sure that it is demagnetized. But if it is, then you will find it very, very easily.
Thank you, Joachim, for nicely explained regarding this question. Now, moving to the round 3 of our session, and again back to our first panelist, Dr. Diego. A very interesting question, sir, for you. Analysis of variable frequency tan delta for bushings and reason behind variable frequency tan delta testing, and why temperature correction for entire frequency range is important.
That is actually one of the hottest topics that we are discussing around. And right now, we just came back from a conference in Italy at the My Transform, and actually, it was a very interesting topic of discussion. The why are we doing this? Just so you know, in IEEE, we came up with a new guide for DFR on bushings, which is the C57-12-200, and that was published just at the beginning of the year. The work was finished only last year. And the idea is when you look into the wide spectrum of your bushing, you can look into what we just were mentioning before to prevent things. The early degradation of the insulation can be detected when we start looking into this wide spectrum of frequencies. But interesting enough, we have seen changes not only on the low frequency range of frequencies, but also on the high frequency range, right? So just being able to step out of just our 50 hertz or 60 hertz tan delta testing allows us to have an understanding of the dielectric changes and some of mechanical issues that we have identified. Especially on the high frequency side, these mechanical things could be a poor grounding on the bottom flange of your bushing. We have identified loose connection of the test tab, right, by means of this type of testing. On the lower frequency range, we have seen this degradation. And actually, the way that we have seen this is that most of the temperature correction, according to different factors, are very close to unity. So you go from 10 degrees up to 40 degrees, and it's 0.999 or 1.00 something, right? So it's very close to 1. There's no changes really for correction factor on temperature. But when you start looking at the dielectric response and the changes on the dielectric response that correspond also to changes in the thermal response of this bushing from the dielectric point of view, you understand that, you know, if everything is linear, you have a good condition bushing. But if changes start happening, that is the important way. That's why we do this correction on the entire frequency range, right? And again, the other thing, do we need to go to very low frequencies? No. That's one of the statements that is coming up, and it's present now on the new standard. You don't need to go below 10 millihertz. First of all, because you're measuring current. And if you have a low capacitance specimen, right, you need to have enough energy to be able to measure this current. So you're measuring a very tiny value of current, right, and a very low value of capacitance. Then you really need to work sometimes with higher voltage. And that's the reason why when we're thinking about bushing testing and this dielectric frequency analysis, we go 2 kV peak, right, to overcome the noise in the substation and be able to get the dielectric response that corresponds to that specific bushing and do a proper analysis, because it could be contamination, it could be moisture, it could be, you know, changes, degradation on the insulation that we want to see before that happens. The other thing that is very important, and something that Dr. Aurora started talking on the C2 analysis, is that most of the time you have 3 bushings on your transformer. So you can do a very good comparative analysis of those 3 based on the dielectric response and take the priority, which one needs to be taken care of first, right? So it's a great tool to have the electrical response, especially for bushings. I know that we have limited time, so I'll stop there.
Thank you so much, sir, for in very limited time, very crisp answer you have given. Yeah. Thank you, sir. So moving to the next question to Dr. Arora, sir. If a transformer or a specific electromagnetic coil insulation is rated for 5 kV operation, what should be the IR test voltage, insulation resistance test voltage, and what will be the allowable leakage current?
Okay, Ankit, thank you very much. And to answer that thing, I can tell you the IEEE Guide C43 2013.
Yes.
That guides in table number 1 elaborate what are the maximum voltage to be given for a particular equipment of a particular voltage. If you are talking about 5 kV, it is 1000 to 2.5 kV allowed. And so far the leakage current is concerned, I can tell you what IR value is. I am giving the fundamental things. Initially, there is some capacitance that get discharged in fraction of seconds. Then there is some conduction, actual conduction, then there is surface leakage, then there is some polarization. Okay.
Correct.
And when all these settles, we measure two values, absorption ratio and the polarization index. Again, absorption ratio internationally is measured for 60 seconds upon 30 seconds, where in India, as per CA guideline, standard guideline, that is 60 by 15 seconds. But that polarization index values remain same internationally and Indian standards, 10 minutes to 1 minute. And it should be more than 4 for excellent value and 2 to 4 is acceptable. Questionable is 1 to 2 and less than 1 is not allowed at all. And so far leakage is concerned, there should not be any leakage. To take care of leakage, we are using guard terminal that take care of the leakage. And if your guard terminal has sufficient capacity to take care of that leakage current, that will be good. I think Megger has that facility to take care of the leakage current, that nullify it and gives you the proper results.
Thank you. Thank you so much, sir, for your answer. Now moving to the next question to Patnaik, sir. And the question is the no load loss of transformer varies with aging? If yes, what could be the reason?
Yeah, actually, it is one of the very interesting question I can say, because maximum of the people, they know that no load loss remains the same for any kind of transformer. But in this aspect, I can say answer is yes, it will vary, because the parameters which judges this no load loss, that is the kind of electromagnetic core what we are using. But in the way of aging, automatically the electromagnetic core will also get a change, because the clamping, core bolt and everything will get looseness. So that also will be judging about the quality, dimension and orientation of that particular core. So that will be affecting to the no load loss. Second point comes, even if you also winding is another factor, because winding dimension also will get a change. May not be of that way, but it is also another way to consider that due to change of this winding, slackening of those winding and all, finally will come for affecting to the no load loss also. And another most important factor regarding the flux change, whenever it happens to be the aging, we exactly cannot expect that the similar kind of things it will be offered by the transformer. So in totality wise, I can say yes, no load loss varies in terms of aging of the transformer. That's all from my side.
Thank you, sir. Thank you for your answer in elaborated way. Yeah. Now moving to the next question, and the question goes to Amandeep, sir. And the question is PD testing. What are the PD testing advanced techniques which is available in the market? Is traditional electrical PD testing is more informative as compared to UHF, especially on transformers?
Okay, thank you, Ankit. I'm afraid again a very it's a
Tricky
topic on
question.
itself.
Yeah.
Yes, PD testing in itself is now subject of many seminars,
Correct.
because this technology is recently being adopted and very rapidly being adopted by the Indian utilities. And I would again try to summarize and for the very briefly for the benefit of the participants.
Yes.
So when we talk about PD testing, advanced techniques, conventionally electrical PD testing is and was being used in the factories. So electrical PD at factory as a part of a factory acceptance test is already very much imbibed into the specifications and the procedures. And besides that, on site, we have got many other options like UHF, ultra high frequency PD monitoring, acoustic PD monitoring, and TEV, transient earth voltage uh, PD monitoring. So these techniques are only varied based on the monitoring and the detecting capabilities of these monitoring techniques is different. For example, for acoustic monitoring, we generally monitor within the range of 10 to 300 kilohertz. And for UHF, we do it from 200 to 1.5 gigahertz, 200 megahertz to 1.5 gigahertz. Then TEV, we do the monitoring from 1 megahertz to 100 megahertz. So these are just no very uh, the the techniques and the monitoring and everything is different, but the end result is all the same. We want to capture whether there is any incipient fault inside our transformer, and because this transformer, when it would have a fault which is just starting and before it develops into a major fault which leads to the breakdown of the transformer, and if we can capture this fault at a very initial stage, so in that case we will be able to save our equipment, very costly equipment. We will able to save the availability, reliability for the system, for the grid point of view. So all these techniques monitor these and try to capture these faults by different way. For example, the acoustic would try to hear the fault. The UHF would try to sense that frequency within the tank, and the TEV, when this signal is getting, hitting the tank of the transformer, some earth voltage is being induced, and it would try to sense that rise in earth voltage, the currents. So these are the different monitoring techniques. And the second part of the question was the traditional electrical PD testing is more informative. So like I said in the opening remark also, as a part of factory acceptance test, electrical PD is well established, but its application at site is somewhat limited due to the disturbance from the other equipment which are in service adjacent to our transformer which is being tested. And secondly, electrical PD testing will only indicate the presence of PD. It would not provide a precise information on where that PD is. See, when the transformer is such a huge job, and first of all, if we have established that there is PD activity going on inside the transformer, which can also be correlated with DGA. DGA is also a method for detecting the PD, because whenever
Yeah.
the PD is occurring, hydrogen and C2H2 and other relevant gases are getting generated. So that factor is already established at site that something is going on inside your transformer. Now you want to detect where it is and whether it is repairable at site or it will have to be taken back to factory for the repair. So for localization and identification of the source, UHF PD is a better option. I am not saying that UHF is the best option. It would also depend on the equipment that you're using for making that measurement. It will also depend on the training and the experience of the personnel who is performing that test. And sometimes you also have to rely on luck, because it is possible that when you are doing that testing at that instance, PD activity is not occurring. It may be occurring at certain voltages. It may be occurring at certain, when some transients are getting generated. So you also have to be lucky in that respect. Your equipment should be capable enough to sense, and the personnel who is carrying out the test should be experienced enough, trained enough to handle that equipment properly. So based on these three factors, I would say UHF PD, talking specifically when we are talking about these two options, is better than electrical PD because it offers us localization and source identification for the PD. So it would be better in my experience. So that is it. Thank you.
But sir, some of the customers like utility experience, they also says that if they will get the opportunity for the shutdown, and then if the sensors are previously installed in the transformer and the electrical PD based on IC 60270 is going to give us more information in terms of localization of the fault.
No, but electrical PD would only detect the signal which is getting generated from inside the transformer.
Yeah.
It would not be able to localize where that fault is. So even if you have established that there is, and of course, electrical PD is much more reliable and it would be continuously monitored. So it would have another advantage.
Yes.
But when you look at a transformer, let us say a 500 MVA, 400 kV job or 765 kV job also, then it's a huge job. You have got already for a 400 kV, you have got 3 windings and winding HV, IV, LV. So we need to localize where the fault is and whether it can be repaired at site or not. So in that respect, electrical PD would give you less input for the asset manager to decide on the next course of action. Of course, it would be very helpful in identifying that PD is occurring, but where it is occurring and whether it can be repaired at site. For those things, UHF or acoustic or TV, so we'll have to take, supplement our results with those advanced tests.
Yeah.
Yes. Yes.
Yeah.
Dr.
Arora sir, you want to add something?
Yeah, I want to say one thing through this very important platform, that what we expect as a utility person. The testing equipment should be reliable, should be robust, should be easy to operate, easy to handle. That should be have capability of to give same result, precision and affordability. And very rightly said by Amandeep ji, it should be capable to pinpoint the particular fault. That as a utility person we expect from manufacturers to come out. With that we can, and finally the last but not least, that should be safe to operate. That should be the main criteria to select any equipment, testing equipment of any company.
Sure, sir. Sure. Yeah. So we are running short of time and we are already behind 10 minutes as per the schedule. So moving to the last question of this particular session, and the question goes to Joachim Skolden. However, moving to the question, before moving to the question, I would like to also address that the question we have got the tremendous response for this, platform, this panel discussion, and we will also try to address the question which has not been taken in this particular panel discussion offline. Maybe in terms of email, we will try to reply and we will take the opinion from the expert and we will also try to reply on this in email. So moving to the last question of this particular panel discussion, and the question goes to Joachim Skolden. Sir, the question is, what is the advantage of DFR test, dielectric frequency response test on transformer winding, and how I can correct my tan delta value taken at ambient temperature to reference temperature 20 degrees C?
Okay, a two-part question.
Yes.
Advantage of DFR and how to temperature correct. First of all, this has been discussed a little bit already by the tests that you can perform on a transformer, but also by Dr. Robalino. I would like to elaborate a little bit on those. DFR, what is DFR? The electric frequency response. It is basically taking a tan delta test at multiple frequencies. Taking a tan delta test has been done for many years, and it is not something new. What has happened is you can now make this tan delta test at many frequencies. What Diego or Dr. Robalino talked about was the bushings, where you do not have to take such a long sweep or such long test with a lot of different frequencies. But if you compare the bushing with a transformer, there is a significant difference, because the bushing is has a solid material. It has an oil impregnated paper, or it has another type of it can have polymer or something like that, but it's still only one single material. While for a transformer, you have two separate materials, free oil and also oil impregnated paper. That creates a difficulty in analyzing the result, because now you're measuring two different insulation materials. So here you have a big advantage of the DFR when you can make this test over a wider frequency range. You have the ability to separate the response from the oil from the response from the paper. Now you can look at the paper response individually and see whether your paper is good, if your oil is good, or and vice versa. This is a tremendous significance benefit. If I just go back to the second part where we look at the temperature correction, how is this relevant for this test? Well, I said it is not a new test. It has been done for a very, very long time, but only at one single frequency. When you have done that test for that specific frequency, you have had a acceptance criteria. If it is above this value, it is not okay, and above this value, it should be investigated, and so on. Now, those acceptance criteria are defined for the insulation material when it's 20 degrees centigrade. Now, if you go out and you take your measurement at another insulation temperature, you will then have to correct your measurement value back to the temperature where you can apply those limits. Previously, it has been done with correction tables, which is a guesstimation. It has been removed. Later in the recent years, they have found that these correction tables are no longer valid. They create a little bit more problems than they give good answers. So what you can do is actually use this frequency response that you have taken and the physics of the different materials, and you can apply that to your temperature corrections and use your measurement to calculate and define how your object would behave for different temperatures. Then you can, of course, correct your measurement back to the 20 degrees, and you can apply those limits and make sure that your evaluation is good. With the DFR measurement, what we see is it becomes less and less significant to use the 20 degrees, 50 hertz or 60 hertz measurement only, because you get so much more information with the whole frequency range. So you get the information you're looking for already with that whole frequency sweep. So the other part is, of course, if you measure the whole frequency sweep, you can also sometimes find irregularities, such as the bad grounding. You can see contamination on the windings. And all of these phenomena is being investigated more and more. And I am sure we have a lot more coming when we start investigating these curves that we are actually getting from this type of measurement. So I could also elaborate more about this, but again, we are already short on time, so I think I should be quiet and hand over to you, Ankit.
Thank you, Joachim, for your wonderful explanation in very short time for the audience. And I hope this panel discussion finds you well, and I wanted to take a moment to express my sincere gratitude for your valuable contribution as a panelist to Diego sir, to Patnaik sir, our special guest, Patnaik sir, Amandeep sir, and Dr. Rajesh Arora sir, and to you, Joachim, as well. Your willingness to share your knowledge and engage in thoughtful dialogue was instrumental in making the event as a successful. And it is evident that your passion for both as well as for the participant is inspiring, and we will do the continuous work towards a benchmark for the electrical industries. So with this note, I would like to thank you once again to the audience, to the panelists for taking time to attend this particular panel discussion. And I am sure that we will also conduct this kind of panel discussion in future coming days. Thank you very much, sir.
Thank you, Ankit. Wonderful session. Very
Yeah.
nicely conducted. Very well moderated. Thank you.
Thank you very much.
Yeah,
Sir.
thank
you.
Thank you, Ankit. Actually, you are one of the pioneer in this regard. So many,
Thank you,
many
sir.
thanks.
Thank you so much. Thank you.
Yes. Right.